Alrighty, so today we are going to start our discussion on electricity. Of course, over the course of your physics career, you're going to get into electricity, you're going to get into magnetism. Eventually, we're going to see that electricity and magnetism are kind of two aspects of a single entity, or at least this is how we can describe it, and that is called electromagnetism. That is to say that while electricity and magnetism seem to be two different things, two separate things that are kind of related, that is to say a magnet produces magnetic effects. You could have magnetic forces. Two magnets can attract each other or repel each other. But also, the same can be said about electricity. You could have electric charges, and two electric charges can either attract or repel each other. How they actually work is quite different, yet fundamentally it seems that although there's a difference in how they work, they seem to arise from the same fundamental aspect of the universe. And that eventually we'll get into induction and things like this. But for now, we're going to focus specifically just on electricity. And in fact, we're going to start with what's called electrostatics. So, just as is true when we discussed in other courses, things like statics and dynamics, engineering courses, and basic general physics, you usually start with kind of the most simplified model, simplified systems, so that you can understand how these systems work and the conceptual basis, and then you start to complexify it by allowing things to now move, forces don't balance, you have accelerations now, whatever the case may be. And it's just an extension to the previous simplified version. Well, the same is going to be true here. We're going to start with systems that have one or multiple particles. Those particles are fixed, they're stationary, and we're going to ask questions about what force would this particle feel, or how would this particle interact with these other particles if we were to turn the system on, let's say. And then later on, you'll get to electrodynamics, which is now you have moving charges, moving particles, and how does the motion of the particles affect things. And that's eventually how we're going to get into magnetism and things like this. But for now, we're doing electrostatics, which basically means things don't move. They're stationary. We set up a system and ask questions about that system as it is, but we don't let time start to move and allow the system to evolve yet. Okay, so how I want to get into this is kind of an analogy. And it's a useful analogy just because, mathematically speaking, how related these two different phenomena are, and that is electricity versus gravity. So in general physics, in regular physics, mechanics, we talk about gravitational forces. You have two objects, so let's look at gravity. Two objects. Here's one, here's another. Maybe this is object one, this is object two. These objects have a certain attribute, and that is called the mass. So this has some mass m1 and some mass m2. And what the mass is kind of a source of this gravitational effect. That is to say, if you have two objects which contain mass, then they will interact with each other gravitationally. So you here on this Earth, you're pulled down towards the Earth because of Earth's gravitational field, because the Earth has a mass and you have a mass. And of course, Newton's third law says if the Earth is attracting you by gravity, then certainly you're attracting the Earth by gravity with exactly the same force. And the reason this force exists, or the reason this interaction can occur, is because these objects have this thing, this source, which is called mass. Okay? And every object which has mass will interact with each other, with other objects that have mass, by this gravitational mechanic. Okay? And what do we know about it? Well, first of all, the force felt between these two masses, these two sources of the gravitational effect, is always, firstly, attractive. So all these sources, all these masses, always attract each other. So the force by gravity is always attractive, and it's always radial. It's always on a straight line path from one mass to another mass. So mass M1 will feel an attraction due to mass M2, which is in the direction of mass M2. It's pulling it towards him. And the direction he will feel, of course, is in that line towards M2. It's not going to be up in this weird angle for some reason. It's going straight towards the other mass. And likewise, M2 feels an attractive force due to M1. And it turns out, like I said, from Newton's third law, that they will feel the same force, just one goes towards the other. But that isn't to say they will move in the same way because of this force. Because F equals ma, right? F equals ma says an object whose mass is m will feel an acceleration a because of this force. Well, if you have two masses, m1 and m2, and let's say m2 is bigger than m1, then if they both feel the same force, but m2 is bigger, that means his acceleration must be smaller, because m2 times a has to be the same number as m1 times a. And if m2 is bigger, then a for m2 has to be smaller, so that when you multiply the numbers together, you get the same answer as m1 times a, just in the other direction. Okay? So they feel the same force, but of course, that's why you fall towards the Earth, but you don't notice the Earth fall towards you. Okay? Your mass is so much less than the Earth's mass that you don't detect the motion of the Earth, even though you are pulling on the Earth, just as hard as the Earth pulls on you. The other thing we know is the form of the equation to calculate how much force an object will feel gravitationally due to another object, and that is F, force due to gravity, is given by some number. Who cares what this number is? It's just a constant, and it has to do with our weird units as humans, meters and seconds and kilograms. Those are all arbitrary units we use here on Earth, whereas some other civilization on an alien planet would have some other set of units. The fundamental aspect of the equation, the form of the equation, will look the same to an alien civilization, but whatever this first number, this G I wrote here, will be some other number for them, purely because when they talk about how much force an object feels, they're not saying how many newtons. That's what we say. That's our weird human unit. Aliens will have some other unit. Now, the answers will match in terms of when I say something like, oh, I'm going to run, 9 feet, or I'm going to run 1 meter. They mean the same thing. It's just that one is in units of feet, one is in units of meters. So the distance is the same, even though the numbers are different. Okay, so anyway, this is just a number because of our units. It's not important. The important parts are, it's the product of the masses. So what are the two things that are trying to attract each other? Obviously, if you have more mass, more of this source of the gravitational effect, then the force you will feel has to be more as well. There's more stuff to attract. And then it's divided by, that is, it's inversely proportional to how far away the other mass is from you, squared. So that's r squared. Okay? So this is the equation for how much force two objects will feel due to the gravitational effect. Okay? So it's some number due to units, whatever that is. Then how much of the source of this effect exists, that is M1 and M2, those are the two things messing with each other. And it's divided by how far away squared the other mass is. The further away the other mass, the less you feel it. The closer it is, the more you feel it. And it drops off as the square. And eventually, when we get to the electric version, we could do this also for gravitational version, but for now, I will just preview that the reason there's a square, it's r squared and not just divided by r, has to do with geometry and how the effect, how this gravitational effect, the force, the feeling due to gravity, drops as it's spread over three-dimensional space. Okay? So the way I've drawn it, you just see M1 and M2 on this line, and the forces are affecting each other in this straight line. But of course, deep down, the actual picture says that there's space that's being bent and being curved by these things. And so the effect of gravity bending the space is affecting all aspects around the masses. All of this is being affected, but the only part of that effect that's felt by the other mass happens to be the effect that's on this straight line. This mass, too, can't feel what's going on over there. It only feels the effect that it can feel straight from the other mass. But that mass is affecting the rest of space around it, and thus you have a geometrical effect. The more space that gravity is affecting, the weaker it's going to feel to you, because most of it's being sent off in a direction you can't feel. So it's being wasted over there. And that's why there's a 1 over r squared. But like I said, when we do it electrically with what's called Gauss's law, we'll see this much more strongly. All right, well, that's gravity, right? Very, very normal in our everyday lives. We know how gravity works. Two objects attract each other with a certain force. The force is a straight line path between the masses. The masses are the source of this effect, and it's always attractive. Okay? Now, electricity is very, very similar. For electricity, we have sources of this electric effect. What's the source of the electric effect called? Well, now it's not the mass. The mass is the source for gravity. The source for electricity is called the charge. Now, the first weird thing about electricity as it relates to gravity is that there's two different sources or two different types of charge. That's not true for gravity. The mass, there's mass. That's all there is to it. There's one type of mass. All objects have that one type of mass. The only difference is different objects have different amounts of it. So some things weigh 5 kilograms, some things weigh 15 kilograms. But a kilogram of mass is the same everywhere. It's mass. With charge, there's two types, two flavors of this source. They both give rise to this electric effect, but the two flavors give rise to that effect in different directions. So whereas for gravity, the source produces the gravitational effect, and that effect is always to attract the two objects together. Always. For electricity, you have two different types of sources. Both of these sources can give rise to the electric effect. However, depending on what these sources are, is it the A type or the B type, which flavor, then sometimes the force is attractive and sometimes the force is repulsive. So we call these two types of sources, these two types of charge, positive and negative. Okay? just names. We had to label them in some way. We could have called them red and blue. We could have called them up and down. We call them positive and negative. Okay, so you have positive charges and you have negative charges. Those are the two types of sources for this electric effect. And every single object which interacts using this electric effect has one of these sources, or multiple. Okay? Now, one interesting thing about the source, the charge source, which is not true, at least classically, in normal gravity, the mass. In gravity, the source of gravity, mass, you can have any amount of mass. So you could have a kilogram of mass, you could have a milligram, you could have a picogram, it doesn't matter. You could use any number of mass. Any number, doesn't matter. You could have any amount. Of course, when we get into quantum mechanics, maybe there's some issues when we talk about that, when we get really, really fundamentally low. However, for our purposes for now, we just say any object in the universe can have any amount of mass. There's no restriction. However, it turns out that for the source of electricity, the charge, every object always has some integer multiple of a particular amount of charge. So you can't have any amount in existence, but rather you could have, let's say the charge, we'll call it little q, that's charge. You could have a q, you could have 2 times q, you could have 3 times q, but you can never have 2.46 times q. Okay? Now what is this q? Q is equal to 1.602 more times 10 to the minus 19 in some units, and that unit is capital C. It's called the Coulomb. Okay? So this charge, I'll put a little subscript E on it, because sometimes you'll see it as little e, sometimes you see it as Q sub E. This is the fundamental unit of charge. It's very tiny, times 10 to the minus 19, that's a very small number, but every object in the universe has some multiple of this number. Okay? This number happens to be the charge of an electron. Of course, the charge of an electron is negative, this. The charge of a proton is the same number. So this is the charge of a proton or electron. Electron has the negative version, proton is the positive version. Okay? So if you have some atom, that atom has a nucleus with multiple protons and neutrons in it and some electrons orbiting around. If you want to know what's the charge of this atom, if you add up everything, depending if it's ionized, whatever, any random atom, if you look at the charge, it's going to be this number times some integer. So maybe 19 times this number, or 0 times this number. You could have neutral objects. That would be weird gravitationally. In gravity, a neutral object would have no mass, right? If it has a mass, it will interact gravitationally. For electricity, if it's got a charge, it will interact electrically. If you happen to have 0 charge, now how you get 0 charge? Well, it depends. Are you the neutron? The neutron has no charge. Or are you an atom that's neutral? So maybe you have 2 protons, 2 electrons. You add them up, you get a total of 0 charge. If you have 0 charge, classically, we would say it will not interact electrically. It would be as if the object has no mass, and thus it doesn't feel gravity. Now, I say that in a simplified way because, of course, when you really look in a detailed fashion, if you have an atom that's neutral, so here's your nucleus, and then you've got the electrons orbiting around, well, yes, the number of electrons and the number of protons balance each other, so it's totally electrically neutral. However, you still have individual particles in this atom that are not neutral. You have protons, and those protons have charge. You have electrons, and those electrons have charge. So each individual thing can still interact electrically. It's just that if you take the atom as a single entity, from a distance, it seems as if it would not interact electrically. You have to probe very, very close to see the effects that there are still charges, even though they balance each other. All right, so fine. Just as in gravity, we have sources for electricity. Weird, we have positive and negative versions instead of just a single version, like mass. But okay, we have two versions of this source. We call them positive and negative. All objects have some amount of charge, whether it's zero or some number, at least as far as we're aware. Now, there are questions about things like dark matter out there, which don't interact electrically. So does that mean there's no existence of charge in its nature? We're not sure. But of the things we know for sure, everything has some amount of charge, whether it's zero or some amount, positive or negative, and it always comes in multiples of this fundamental charge number. Okay? All right, next, how charges, these sources, so here's Q1 and here's Q2, how will they interact with each other? If these were gravitational particles, that is to say these are masses, then I told you, the masses affect the space around them, bending space and time, and because of the bending of the space, the other particle will feel this bending in space and will move through this bent space in a way that makes it look like there's a force between the two particles. That is to say, mass m1 is attracting mass m2, pulling each other together. And the line is always the straight line distance between them, and it's always attractive. Electricity, what happens? A very similar effect. Okay? For now, I'm not going to talk about the warping of space reversion, but there is something like that, and that's called the electric field. We'll discuss the electric field in the next video. But basically, it produces this field around it, and that field will kind of interact with the other particle. That particle will feel something from the field and say, oh, I'm going to move in this direction or in that direction. And it turns out that, just like with gravity, these particles, these charges, affect the field all over the place, three-dimensionally. But what the other source, the other charge, will feel happens to be the amount that's affected in the straight line between the two. So just like before, you're going to get some force that's on the straight line path between them. The question is, will this force be attractive or repulsive? And this is where the two types of charge thing comes in. The way you figure out if these two sources will be attracted to each other or repulsed by each other, that is to say, which way will the force push them, is, the rule goes, like charges repel, unlike attract. Okay? So firstly, this is automatically different from gravity. With gravity, you only have one type of source, so all these masses are the same, so they're all like masses. And we know that the force is always attractive. So for gravity, the source of gravity is the mass. There's only one type, so they're all the same. And if you have two of the same types, that is, you have two masses, they attract each other. Electricity, we have two types of sources, positive and negative. And it turns out if they're the same, like with gravity, they actually repel this time. So if these two charges happen to be positive charges, then of course Q2 will be repelled to the right and Q1 will be repelled to the left. Or if they're both negative. Okay, it doesn't matter if they're both positive or both negative, they act the same way. They're repelled. Now, if one is positive and one is negative, then they will attract each other. Okay, so as if it were gravity, two masses always attract each other. For charges, if they're unlike charges, that is, one's positive, one's negative, they will attract each other. Which is the positive, which is the negative, doesn't matter, as long as they're opposites. And that better be the case, because who the heck came up with the names positive and negative? If it mattered, oh, the positive one always acts this way and the negative one always acts this way, then we have a problem, because, well, the universe didn't tell us which one is the positive one. We just named it. We said, oh, I'll call that one positive. We easily could have said protons are negative. We could have called the protons the electrons and the electrons the protons. It's just an accident of naming that we named it the way we did. So it doesn't matter which is the positive, which is the negative. We just know they will attract each other. So if you have two random charges and you put them next to each other and you see how they act, you can't tell which one's positive, which one's negative. All you can tell is, are they the same or are they opposites? Are they both positive or both negative? Or is one positive and one negative? You can't tell which is which, though. Okay? All right. So, that's very nice. Electricity seems to work very similarly, with some differences, to how gravity works. And indeed, it's very nice, because it turns out the equation to calculate how much force these two charges will feel when they interact, it turns out that this is what's called the Coulomb Force. The Coulomb Force is defined, I'm just going to give it to you for now, as some number. Don't worry about what this number is. Just like with gravity, it's a number that has to do with our units and things like this. Okay, so some number times the actual sources of the electric effect, the Q's, Q1 times Q2, divided by how far apart the two charges are squared. Almost identical. Look at this. Here's the equation for gravity. G m1 m2 over r squared, the product of the sources divided by the square of the distance. For electricity, the product of the sources times divided by the square of the distance. Identical form of the equation. Very, very nice. Another thing we have to worry about is this is a vector equation, which means directionality is going to matter. Of course, if we just have two charges, let's say we have here's a charge and here's a charge, and we want to know how they interact, well, we could say, okay, the force is this way, it's got some x component and some y component, and do the x and y component stuff. Or you could be smart, and as you get more and more experience, you notice tips and tricks like this. We could just take this problem and rotate it so that instead of it being at this weird angle, it just looks like they're one to the side of the other. We just rotate this thing so they're all on the same line, so we don't have to worry about the angles anymore, because the force is always on the straight line distance between the two charges. Okay? You could always rotate your coordinate system. But where it will come into play, much more importantly, the fact that this is a vector equation, is when you have more than two charges. So maybe you have a charge here, and a charge here. And you want to know how much force will this guy feel. Well, he's going to feel a force due to this guy, and he's going to feel a force due to this guy. Okay? Obviously, if these two forces, if we need to add the effects together, and we'll find out if that's true, then we're adding vectors together, and we know the rule for adding vectors. You have to get x and y components and all of that. So this is a vector equation, and that's going to be very important, but the form of the equation is very simple. All right, so let's look at a particular example. Very easy example. Here's our coordinate system, x and y, and let's say I have a charge q1 and a charge q2. Okay, let q1 be 2 times 10 to the minus 6 coulombs, and q2 is minus 3 times 10 to the minus 6 coulombs. Okay? Excuse me. And the question is, find the force on 1 due to 2. This is my notation. Okay? Whenever I do something like this, the way you should read it is the force felt by the first number because of the second number. Okay. Be very careful when you're looking online and textbooks. Different professors have different notations. Some people would read this in the opposite way. What's the force felt by 2 due to 1? Okay. For me, I'm telling you, whenever I write this down, this is what's going on in my head. The force on 1 due to 2. All right, so first question is, before we even calculate anything, let's try to get an idea of what we expect to find. Okay? We should always do this in physics. That's why we're not just pure mathematicians. We actually have physical processes here, which means the answer I should get should make physical sense. I should have some expectation, if possible, about what the answer should look like. I may not know the answer, I may not know the exact value, but at least I know how things should work. So when we look at this, I'm told Q1 is a positive charge and Q2 is a negative charge. Okay? First thing I know is that these charges will attract. Okay, so I know they will attract, which means Q1 is going to be pulled to the right, and Q2 is going to be pulled to the left. That I know. So when I get my answer, I should expect an answer for Q1, because that's what I'm looking for. How much force will 1 feel because of 2? I should get an answer that says it moves to the right. So I should get a positive force. If I get a negative force for Q1, I know I did something wrong somewhere. Okay. Now let's find out what the actual answer is. The force felt on 1 due to 2 is some number k times charge 1 times charge 2 divided by r from 1 to 2 squared. Okay, now I'm putting this little notation on the r as well, because eventually when we have more than 2 charges, we want to keep track of these distances in an easier fashion. So this is the distance between 1 and 2 squared. All right, now, first thing, what is this k? This k, I'm just going to give you the number, is 8.99 times 10 to the 9. It's a constant. What I'm going to use, just to make calculations faster, is I'm just going to call it 9 times 10 to the 9. Okay? So it's easy to remember. 9 times 10 to the 9. Now, where does this number come from? It actually comes from a bunch of different things, okay? But usually it's written in the form 1 divided by 4 pi times some other number called epsilon naught. This epsilon naught, which is called permittivity of free space basically tells you how easily will this electric effect move through the medium we're talking about. So if you remember when we do optics, light has a certain speed, but it has a certain speed that's different in each medium. When it goes through air, it goes at 3 times 10 to the 8. But when it goes through water, it goes at some slower velocity. And the index of refraction tells you basically the difference or the ratio between the actual speed of light in vacuum and how fast it goes in this new medium. Okay? Same kind of thing here. This number, this epsilon naught, permittivity of free space, is for the medium we're in, which is free space, vacuum. That's what we're assuming in this problem. How easily will the electric effect move through it? It eventually will tell us something about the speed of light, the speed of the electric effect. However, for now, just think of it as one of those numbers that tells you about the medium you're in. If we're not in free space, if we're in water, if we're in glass, then that epsilon naught will be some other epsilon, which is some other number. But what is this number, if you want to know what it is? I believe it's 8.85 times 10 to the minus 12. Okay, so if you put 1 divided by 4 pi times this number, you should get something like 9 times 10 to the 9. Now, that's just a constant. Okay, it's always this number unless, like I said, we have more complicated questions later on where you have this set of charges and we're going to put these charges in glass or we're going to put it in water, and then we want to know how will electricity affect things. Then we'll use a different number. But for the vast majority of our problems, this kappa, this k value, is always going to be this 9 times 10 to the 9 business. Now again, let me just go and show you something very nice, which we will see later on. It'll become more important later on, but for now, it helps you visualize why does this equation look like this. And really what this equation is actually 1 over epsilon naught, so what medium are we in, times 1 over 4 pi r squared. This term tells you this effect dies out the further out you go, like the surface area of a sphere. That is a 3-dimensional object. The further out you go, the less effect you're going to feel. And it goes by this 1 over 4 pi r squared business times the product of the q's. Okay? So, kind of 3 terms. The force felt by a charge due to another charge depends on what medium are these charges in, so how easily does this effect happen. It's multiplied by an effect due to how far apart they are, and it turns out that the force dies out as if you have a sphere growing in 3 dimensions. The bigger the sphere, the bigger the surface area, which means if you take $100 and you spread that $100 among 1,000 people, everybody gets less than if you spread it over 10 people. So the further out, if this charge has an effect that kind of goes around him like this, well, eventually when it hits that charge, this Q1 feels an effect, or let's say Q2 feels an effect from Q1 that's been diluted because that effect is spread over this big, huge circle. Whereas if it's really close to this first circle, so the 2 charges are very close to each other, then that force is diluted over a very small amount of circle. Okay, of course, we're talking about 3 dimensions, so it's a sphere. That's why it's 1 over 4 pi r squared, and not 1 over 2 pi r, the circumference. But this is a way of thinking about the Coulomb force equation. An effect due to the medium, an effect due to how the force dies out because of distance, and then what are the sources causing this effect, Q1 and Q2. The easy way to write it, and the way you usually see it, is the blue one, though. Some number k, that's the 9 times 10 to the 9, times q1 times q2 over r squared. Okay? So let's go ahead and solve this problem. We have, I'll redraw it here, q1, q2. Let's say these two charges are 4 meters away from each other, so very far away. Q1, I'm told, was 2 times 10 to the minus 6, and Q2 was minus 3 times 10 to the minus 6. I already said in my head, I know Q1 will be pulled to the right due to Q2 because they're unlike charges and thus they will attract each other. If they attract each other, Q1 moves to the right. Of course, if I were looking at Q2 instead, then it's the opposite. Q2 would be moving to the left because it's attracted towards Q1. But I don't care about what Q2 is doing. I care, what does Q1 feel? And now my equation, F equals kappa times Q1 times Q2 over R12 squared. All right, so kappa, 9 times 10 to the 9, times Q1 times Q2. Now, here's a rule that's extremely important. I don't write it in the equation. I'm going to go back for a second. But actually, the equation has absolute value bars around the Q's. Okay? I don't like writing that just because it makes the equation look messier. But technically, here's the rule I'm giving you. Whenever you use this equation for force, when you write in the charges, you never write in negatives. Even if the charge is a negative charge, just write it in as positive. Okay? And I'll tell you what to do with the negatives later. So Q1, 2 times 10 to the minus 6. Q2, 3 times 10 to the minus 6. Notice I'm not putting a negative. Divided by the distance between 1 and 2, I'm told is 4 meters. So that's 4 meters squared. Okay? Now is when I take into account negative versus positive charges. So all the numbers I wrote in, I always write in as positive numbers. And now I'm going to place a negative or a positive out in front based on what it should be. Okay, this is how you have to do it. If you don't do it this way, then half the time you're going to get the wrong answer. If you just try to stick the actual charges with their signs in this equation, it will not always give you the right answer, unfortunately. So you have to do this one little bit of thinking about it before we calculate. And this is why I said always think about the problem before you go calculate anything. I know Q1 is attracted towards Q2, so Q1 should move to the right, so I know this should be a positive force. So I leave it as positive. However, let's say it's the opposite. Let's say Q2 was a positive 3. Okay, so if Q2 was not negative 3 but positive 3 in the problem, the numbers I wrote are still the same numbers. That doesn't change. But now I know since Q1 and Q2 are both positive charges, like charges repel, so that means Q1 would want to move to the left. Well, I need to show that in my equation, so I'd put a negative in front of my equation. Okay? Notice both charges are positive, so if I were going by the rule, you just stick whatever sign is on the charges, I would put both charges as positive, yet I know my force has to be negative, and my equation can't give that to me. So instead, I, as the physicist, not only write down my equation, but I think about it, and I say, okay, which way should this charge move? Because they attract, that means Q1 is going to move towards Q2, which is to the right, so I put a positive for the force. He's a positive force. All right, so anyway, there's my equation. Now I just want to go ahead and type all this in. So 2 times 10 to the minus 6 times 3 times 10 to the minus 6 times 9 to the 9 divided by 16. And I get a force of 0.003375 newtons. Positive, notice. And that's my answer. That's how much force Q1 will feel due to Q2. So let me write it in here. Force 1 because of 2. Now, what would have happened had I asked what is force on 2 due to 1? Okay, we'll write down this equation, kappa Q2 Q1 over R21 squared. Well, is there any difference between these two equations? The only difference I see is that I changed the order of multiplication of Q1 and Q2. Instead of Q1 times Q2, I wrote Q2 times Q1. But we know for normal numbers, scalars, which these are just charges, they're scalars, the order of how you multiply numbers doesn't matter. It's commutative. So that means these two situations will give me exactly the same force. And of course it should. That's what Newton's little third law says. Third law says if you apply a force F to an object, that object does the same exact force back on you. So if 1 feels a force of 0.003 because of 2, that means 2 has to feel exactly the same force because of 1. But notice Q2 is attracted towards Q1, which is to the left. So when I plug these numbers in, 9 times 10 to the 9, Q2 is 3 times 10 to the minus 6. Again, I didn't stick the negative in here. Times 2 times 10 to the minus 6. All divided by the distance between them squared. But because I know Q2 will be moved to the left towards Q1, I stick a negative out in front. So now when I plug these into my calculator, I get negative 0.003375. Okay? So that's the Coulomb force. That's the Coulomb force between two charges. They could be like charges, they could be unlike charges, doesn't matter. The equation is the same. The direction you put on yourself at the end. Is it going to move to the right or is it going to move to the left? And the way you figure that out is you look at the system. Are these charges like charges? If so, they repel each other. Whether they're both positive, both negative, doesn't matter. They will still repel. If they're unlike, they will attract. So you just use that to figure out, is it going to move to the right or to the left? Is attracting moving it towards the charge or away from the charge? Obviously, it moves it towards the charge. That's what attracting means. Now, next time, we're going to look at more examples of this, but more complicated examples. I kind of previewed it a little bit. Let's say we had the situation of 3 charges. So Q1, Q2, and Q3. So maybe this is some distance R13, this is some distance R12, and we know the Q's, and maybe the question is find the force on 3, the total force felt by charge 3. We're going to find out how do we solve a system like this, because there's 2 options. We may live in a universe where this is very easy. We already know the rules. If you know how to find the force between 2 charges, then to find the force between 3 charges, then we just think about it as the force on 3 due to 1 and the force on 3 due to 2, and we add those 2 forces together. That would be called the superposition principle. We treat each set of charges as its own little entity, add up all the effects from each set, and that's the total effect felt. The other option is we can live in a universe where the superposition principle does not hold. And in fact, we see that a lot in quantum mechanics and very complicated nonlinear systems, where each individual aspect gives rise to an effect, but when you add up all the effects together, that's not the same as the total effect felt. That would violate the superposition principle. So what we're going to find is, thankfully, we live in a universe where it does follow the superposition principle. So when we want to find the force on 3, that's going to be the force on 3 due to 1 plus the force on 3 due to 2. And these are going to be vector forces, which means I'm going to have to add up the vector forces to get the total, which means I'm going to have to worry about x and y components and things like this. So while this problem is certainly more complicated than this one, it starts with the most basic things, exactly the same. If you know how to do 1 to 2, then you know how to do 1 to 3. And if you know how to do 1 to 3, you also know how to do 2 to 3. It's just that it looks like it's at this weird angle. So we'll have to figure out, well, how do we take into account the angle? But however we do it, once we do it, we have the effect due to 1, the effect due to 2, then we just have to add these two numbers together. They're not numbers, they're vectors, so we have to add the vectors together, but that's going to be the principle. Okay? That's what we'll see how to do next time. From there, we're going to get into what's called the electric field. And the reason we want to do the electric field is because eventually we're going to be working with problems that have tons and tons of particles and one particle over here, and you want to know what will this guy feel due to all of these other particles. Well, we're going to find that just this simple system here with only 3 is aggravating to solve. It's got lots of steps, it takes a lot of time, it's not fun. Can you imagine if you have 100 charges you have to add up together? That's going to be very difficult. So we're going to find little ways of simplifying the mechanics of it without simplifying the theory. We're going to show that there's little simplifications we can do that give rise to exactly the same answers. Okay? But anyway, that's all I have for today. We saw how to find the force due to 2 charges. Next time we will find the force due to 3 charges and continue from there.